Here we go with part 6, which should wrap up chapter 8 here. And while I'm thinking about it, not only is all of this material covered in the corresponding sections of chapter 8 of your textbook, it's the first 11 sections, but you do have practice exercises that are assigned from the syllabus to work on, as well as a few worksheets to help you get straight on the kind of things that you will eventually have to answer on a test. These last couple of slides just kind of sum up what's important about this chapter, especially in comparing these two mechanisms and recognizing their differetions. SN1, again, is synonymous with creating carbocations, and so alkyl halides that can create stable carbocations, they tend to go by that mechanism. That includes tertiary alkyl halides and many secondary alkyl halides, and what also speeds up such reactions is putting them in a solvent that stabilizes carbocations. And these polar protic solvents like water and alcohols, they're really good at doing that. Carbocations maintain a high degree of reactivity, but you need them to exist beforehand if you're going to be proceeding by that SN1 mechanism. And so polar protic solvents are really good for doing that. In contrast, SN2, no carbocations. The big deal is whether or not that concerted mechanism can take place. If the nucleophile can find space to come in and attack the carbon at the same time their leaving group is coming out the other side. So the steric effects, the size effects are important. So tiny methyl groups work well, or any primary alkyl halide works well in that regard. And correspondingly, the polar aprotic solvents go well with SN2 because they don't bog down the nucleophiles, and yet they keep everything dissolved so it can mix together and give a chance for that reaction to take place. And then finally, with the stereochemistry, again, SN1 is oftentimes identified by the presence of a racemic mixture from a starting alkyl halide that may have been one enantiomer or the other. That's good evidence that a carbocation has formed along the way because it scrambles that stereochemistry. Again, for SN2, good evidence of that is when you can get 100% inversion of configuration from a chiral starting material. That kind of lets you know that you didn't make a carbocation along the way. One final thing about carbocations here at the bottom, and when such things were discussed way back in chapter 5 and 6, this was pointed out. Carbocations can sometimes rearrange. If you have a secondary carbocation, it will sometimes shift a hydrogen, shift a methyl group, and turn itself into a tertiary carbocation, which means you've got a different carbon framework in your product from what you had in the reactant. And when that happens, that's again evidence that a carbocation formed. And rearrangements are a nuisance because, generally speaking, we don't want that kind of rearranging to happen. So you kind of have to put up with that possibility for conditions that favor SN1. With SN2, I mentioned that we can pick our nucleophiles because, unlike in SN1 where the solvent is often the nucleophile, that's generally not true with SN2. Those polar aprotic solvents are not very good nucleophiles themselves, and so we can control the reaction in that way. And also, because we don't get carbocations forming in SN2, that means we don't have to worry about rearrangements, and generally that's a good thing in the world of chemistry. So as it references you down there to table 8.10, all of these points are expanded upon in more detail in the textbook. And again, you've got some exercises assigned from the textbook to keep you on track, as well as some problems on the worksheets as well. So good luck with those.